In this video, we're going to cover a short topic on the states and phases of reactants and products in chemical reactions. So overall, we have two main goals. It's first to remind ourselves how to structure our chemical reactions, and then we'll talk about the three main phases and kind of the one side phase when it comes to reactions. Really what we're doing here is we're answering a question, which is these little symbols in parentheses that we've seen in a couple of reactions. We want to explain what they are and why we use them. So overall, the structure of chemical reactions, we've seen a lot of these so far. As a reminder, on the left side, we put our reactants. Those are our starting materials. And on the right side, we put our products. And this arrow shows the reactants becoming the products. So we can see in this case, H2, hydrogen, plus O2, oxygen, creates H2O, or water. So if we break this down a little bit further, our two reactants here, hydrogen and oxygen, these are both gases at normal temperature. Oxygen, we know, is a gas. We're breathing it all the time. And hydrogen, we've generated that in some labs in the past, and we've seen that it comes out of usually a liquid as bubbles. We know it's forming a gas. So in our reactions, we want to indicate this. And the way we do that is because these are both gases, we'll write in parentheses a little g after each of these to show that these are gaseous reactants. On the right side of our reaction, we have water, which we know is typically a liquid at normal temperatures and pressures. So just like the gases, to indicate that our product is a liquid, in parentheses, we put a little L. And usually we use a cursive L, like so on screen, to make it clear that it's not a 1 or a lowercase dash or something. Now, this is pretty intuitive. Gases we label with a G after each reactant or product. Liquids we label as an L, but it can get a little bit tougher. Let's take a classic example, a baking soda and vinegar volcano, a reaction you probably saw a long time ago. If I show that reaction, on the left side, we have our baking soda here and our vinegar right here. And we're going to create three products: water, CO2, carbon dioxide, and sodium acetate. Now, some of these are pretty obvious. The baking soda we know is a solid, so just like we did on the previous slide, we'll put a little symbol after baking soda. It's a solid, so we'll use S. Our water we know is a liquid, so just like on the last side, we'll indicate that water is a liquid with a lowercase l. Carbon dioxide we know is a gas, and it's invisible, so I can't get an image of it. It usually comes in these canisters. But that CO2 that creates the bubbles of that volcano, since it's a gas, we'll put a little g afterwards, a lowercase g, to show that it's a gas. But those other two parts of this equation, the reactant and the product, the vinegar, it's technically not a liquid itself. It's dissolved in water. So what do we put after vinegar? And that product, sodium acetate, that we oftentimes kind of ignore, it also is dissolved in the water. It's in fact dissolved in the water of the product, along with some water the vinegar was initially in. So what do we do about these two components, the sodium acetate and the vinegar, that they technically are dissolved in water? Well, they're going to be that final state or phase that we have to deal with. On this slide, we have a slightly different example, but it's going to illustrate that same concept. In this case, we have a solid copper wire. You'll see the GIF will reset in just a second. We have a solid copper wire that we immerse in a solution, so it's dissolved, of silver nitrate, that clear solution towards the beginning of the GIF right here. That's our reactants. The solid copper wire gets that S because it's solid. But this silver nitrate, that is a solution. That silver nitrate is dissolved in water. And we have a special marking for that. That silver nitrate being dissolved, we say that it is aqueous because it's dissolved in water. So we give it the symbol AQ to show it's dissolved. On the right side, we can see that silver precipitating out, and that's a solid. We can see it. It's solid in that liquid. So we'll give that solid silver the little S, and the copper nitrate that is also dissolved, it's that blue liquid at the end. Because it's dissolved, we'll again give it that AQ. So to be clear, we use that abbreviation AQ to show that something is dissolved in water, and that stands for aqueous, because we're talking about the aqueous phase. Now, these are pretty straightforward examples, but really when it comes to determining states and phases, sometimes it's easy. For example, if we add magnesium to hydrochloric acid and form hydrogen gas and magnesium chloride, we can see that solid magnesium metal bubbling around in that solution. And the bubbles are that hydrogen gas. So we could label the magnesium, it's solid and we see it. We could label the hydrogen, it's a bubbling gas, so we know it's going to come out as a gas. But the clues as far as HCl and MgCl2, they're a little bit more difficult. Sometimes we need to look up what state or phase a material is in at the reaction temperature and pressure to determine what state and phase it actually is. We sometimes have those visual clues, but not always. In this case, the hydrochloric acid is actually our aqueous phase, it's dissolved in water, and that magnesium chloride, one of our ionic products, is also dissolved in the water at the end. These are things we oftentimes have to look up, and we can't just have clues for. And that's going to be it for this presentation on states and phases in reactions.